comment about being live, and then we can go on. Go live. I should have something that should be live. Yeah, it is live, and I can say, and we are live, and we are live. Amazing. Okay, cool. Another one, second one of the day. December is gonna be hard. We're gonna push really hard and see what happens. As always, introductions, common information out of the way. My name is Zach, and I'm an open source software developer. I spend most of my time working on embedded systems, or the interfacing between embedded systems and basically host devices. Quite a bit of my last few months has been spent on working on USB and learning USB and working on image sensors and FPGAs. So those are the three things that really interest me. So I work on video, I work on image sensors, and I try and learn how to use USB and FPGA. And most of this is done in context of Zephyr or Linux, or however way you're going to put this up. And with FPGAs, I do very well. Okay, so that's the general information out of the way. Let's cool. So what are we going to do today? What I wanted to do today was take some time and with an audience, try and go through the protocols that USB uses to communicate. And this is kind of the stuff that we need to understand in order to be able to get to a point where we can make USB devices and USB hosts and things of the sort. I forgot to tell the group that this is live. So I'm gonna go there, and I'm gonna go that, and I'm gonna say to general. Please general. This is live. No. I think in general, the correct general. Yeah, cool. Awesome. So what I wanted to do today is sort of discover these protocols. Well, first of all, what does protocols mean? I think protocol means rules or something. Protocol meaning. I think it's like a way of doing something. What is the English definition of yeah, obviously. So the forms of ceremony or etiquette observed by diplomats or heads of state, code of correct conduct, first copy of treaty and such. So the meaning of a protocol, a system of rules that explains the correct conduct and procedures to be followed in formal situations. So once you have that, this starts to look very demystifying. So the thing I'm discovering about USB is that it has, well, as the article in front of me says, and that you can see on the screen, says USB is layered on quite a number of protocols. And these protocols define how data is sent and is received by between the host and the device. And the host being the big machine and the device being the small machine. Although we are going into a world where USB OTG, USB on the go, has been introduced, and USB on the go has defined. So USB OTG, and USB OTG basically enables small devices to allow to become. Let's look at this, the wiki one. I like the wiki ones. So it basically allows the mobile devices to become hosts as well. They can define themselves as hosts. They can use host roles when communicating with other devices, or they can do some sort of peer-to-peer stuff. Okay. So that was just a segue into explaining this. What we really want to sort of explore today is this system of formal rules, this system of formal things that has to happen in order for data to be sent from a device to a host and from a host to a device. Really, because once you understand why these things have to happen and where they have to happen, then it becomes quite easy to start visualizing USB drivers and how they work, And then additionally, if you have to debug something, if you have to make sure something works, you know where to check, because you can see, you can kind of have an idea of where things happen and such. Um, so, and so on and so forth. And as when you make big networks of these things, you're going to encounter a lot of problems. The other day I was building this little USB applications. USB 6 host experiment, and I built this thing, and it just basically speaks to a Zephyr device that I have here, but that is sold somewhere else. Actually, I should pull that out. Maybe we might end up using it. So I'm gonna pull it out, because if we end up using it, then at least we have a device that we can use to talk to, and we can see what happens. The device in question is an STM32N6. Okay, so we might not even get to the device, but if we do get to the device, that's fine. My point today is to more understand these rules that are set up and that are being used by USB. So let's get started. Let's get really started and see what happens. So USB devices, the USB protocol is sort of, USB itself runs on quite a few layers of protocols, and I've said this already. But you don't really necessarily have, as a designer or as a developer, you don't really necessarily have to know and operate each one of these rules or protocols that are being handled, that USB needs for it to be handled. But it is very beneficial to understand that they exist and where to look for them, so that you can first of all respect them when need be, and also build upon them when you need to. But quite a few of these protocols will have been taken care of by whatever USB IC you're using. So USB has, you need a peripheral device. You either need a host device, or a device that can have a host class on it, or you need a device that implements a device class. And between both of them, one of those circuits, integrated circuits that you get, is going to be handling quite a few of these protocols. So what we're going to do here is just talk about them and understand why they exist and how they exist, and then we'll just leave it at that. And probably next time we'll start actually working on some code, which will be some sort of device driver, I think, or something of the sort. Well, we'll see. We might end up working on a new device driver. We might end up fixing a device driver that I'd rather work on initially fixing a device driver that already exists, rather than actually trying to go out with a new device completely. Okay, so let's think about it. So the one thing that we need to sort of realize about USB is that USB devices, or rather USB itself, is a host-centric bus. And what does that mean? It means that the host actually defines everything it does. It's almost like the SPI device, serial peripheral interface devices. SPI devices, the SPI controller tells the slave or the client what it wants to do. The SPI controller, the SPI master, the SPI bus master will actually send read commands, send write commands, send status commands, and all of those things. And the only thing that the device will do is that it will actually provide ways for it will just respond to those calls by the master. So the host will send a thing called a token packet in the first place, which is a header, and this header will contain what operations it wants to do, whether it intends to send data or receive data, or whether it what does it want to suspend the device, what does it want to do. Okay, and then it might also end up sending a data packet with that header, and then additionally there could be a status packet, which is sort of used to, it's like a handshake. It's used to check whether the thing is done or not. So let's look at what these packets themselves contain, and then we can start actually defining. We can start actually breaking down. So today we'll look at the protocols and the endpoints, and then after that we're at a point where we can actually start approaching some code, especially from the device side, because the device sort of comes with instructions of how to use it, and the host has a way, it already knows how to do some class of things, and the device comes with the instructions of how to use it. So what are common USB packet fields? And today I'm looking through beyond logic. This is a really nice USB kind of document that I found that actually breaks down USB into like very simple things. Okay, so let's look at the common packets that are found in USB. So data on the USB bus is transmitted LSB fast, so least significant bit fast, and USB packets usually consist of one of the following fields. All packets must start with the sync field. The sync field is 8-bit long, and at low and full speed, and 32-bit long for high speed, and it's used to synchronize the clock of the receiver with that of the transmitter. So the transmitter being whichever side of the bus that we're on. And the last 2 bits indicate where the PID field starts. Okay, of the last 2 bits of the sync indicates where. The PID stands for the packet ID. This field is used to identify the type of packet that is being sent. Remember, we talked about the token packet, we talked about the optional data packet, and we talked about the handshake packet. There's the status packet. So there's an out token, which is, remember when we were writing, an out token is for if I recall correctly, an out token is for define read by collecting from the EP in. So in is to read from the device as a host, and out is to write to the device as a host. So whether this is an out token or an in token, so this defines whether it's a write or a read, and then an SOF token, which means this is a start of frame token, and then a setup token, which means now I'm setting up the device or something or so. And then there's the data 0, 1 all the way to 2, and then there's M data, and these are just, you know, this acknowledges which data and such. And then we have an ARC, a NAC, and a stall, and like it's like a clock. It's like a clock code. It's like a I'm still busy. I can't respond yet. I'm still busy with something and I can't respond yet. Packet ID. And then we have a preamble, and we have an error, and we have a split and a ping. And in order, because all of these PID values are 4 bits, what we do is you make it, all the bits are complemented. And I learned about complemented in complementary PWM things, complementary PWM. And complementary PWM means one is high and the other is low. Basically, that's really what it means. So here it is. So one is high, the other is low. One is high, one is high, the other is low. One is high, the other is low, and such. So that's how complementary PWM works. And when they say here that there are 4 bits to the PID, however, to ensure it is received correctly, the 4 bits are complemented and repeated. So this is the high bit, the high bit, the high bit, the high bit, and the low bit, the low bit, the low bit, the low bit. Whatever high and low means in this context. So that if this is 0, this is going to be 1. If this is 0, this is going to be 1. If this is 1, this is going to be 0. If this is 1, this is going to be 0, and vice versa, and vice versa. Basically, they are opposites of each other. And this is kind of to ensure that we are noise robust to noise and things of the sort. So this is basically ensuring that we get the PIDs correctly. And then each packet will also have an address field, and the address field specifies which device the packet is designated for, being 7 bits, and the first address being out loud because it's for devices that have not been given an address yet. So here we can start seeing what happens. So you plug in a device, a setup is run, and then because the setup is run, an address is accorded to this device. This is something that most serial devices don't do this. I2C or SPI or whatever UART, they all have a defined. The device will usually have a defined address. Whereas in USB, the device wouldn't have a defined address. It will arbitrate, or it will negotiate for an address the moment it is set up by the host. Okay, so in essence, what is happening here is that the address 0 is reserved for devices that do not have an address yet, and which are basically going through a setup phase. So anything that you send to address 0 goes to all the devices that do not have an address yet. Okay, so if you have a device on the line and it doesn't have an address yet, it will be accorded address 0, and this is kind of like we're starting to see protocols in action actually, because we're building an intuition here which shows us that once you plug in a device, before it is identified, before it is run setup, if it needs any special sort of setup, before all of those things are run, it's just given an address 0. And once it's run completely and an address is selected, it's given an address between 0 and between 1 and 127, basically, or rather between 1 and 128, because each address is going to be 7 bits, and the 0th one or the first one is taken. Okay, and then we have an endpoint field which is made up of 4 bits, allowing for 16 possible endpoints. Low-speed devices, however, can only have 2 additional endpoints on top of the default pipe. We will check out about pipes just right now, but we will see. Remember when we were looking at control R, LSB, LS. I think it was something like control R, LS, USB dash. Yeah, something like this. I don't know what this was, but you can see it has one interface. This one has one interface. So number of interface. This one has 2 interfaces. LS USB. Let's see how many. Let's look at this Aura controller. So this is 1, 2. It's got 2. Let's look at maybe this phi. This phi 1, 4, 1, 4, 1, 4. And you can see it has several. It's going to have like how many interfaces? Number of interfaces 4, and then in each interface is going to have as many endpoints and such as such. We're going to define endpoints just now. So 4 default, 4 maximum endpoints, and some can have 16. So it depends on either if it's a low speed or a full speed or a high speed device. And then each packet will also have a CRC, which is a hash generated from the data that has been sent, so that the thing on the other side can actually validate that the data that it is receiving has not been messed with, has not been, if there's a man in the middle on the line, we want to validate that there's no one has sort of corrupted the data before it got to the other side and such. And then it has a end of packet field, and this end of packet field is signaled by a single ended 0, which for approximately 2 bit times, followed by a J for a 1 bit time. And these are all defined in, I think I saw them here in USB communications, and we can see what these are. So a single ended 0, both D plus and D minus are 0, and a J, same as idle line. This is present during transmission. Line transmission, alternatively it's waiting for a new packet. So these are all things that exist that you can refer to, that you don't have to find out by yourself, basically, in short. Okay, so now we know common fields in packets, common packet fields. Okay, so let's go and look at what types of packets exist when we're sending when we're using USB communications. So USB has 4 different packet types. Token packets indicate the type of transaction to follow. Data packets contain the payload. Handshake packets are used for acknowledging data or reporting errors. And the start of frame packets indicate the start of a new frame. Okay, cool. So let's look at it. So token packets informs the USB device that the host wishes to read information. Is that what we're doing here? So define read from device by collecting data from endpoint in. Okay. Out informs the USB device that the host wishes to send information. Define write to device by writing to EP out, endpoint out. And then setup is used to begin control transfer. So if you need to like unplug the device, so sometimes you can plug in a device and then you can unplug it. If I do, I think I have a flash drive here. If I have a flash drive here, and I'll do something like this, and I'll plug it in. And it will show up. Here it is. It will show up. It's as a volume. And then if I do something like that, it can be safely unplugged. But let me take it out. Actually, that's actually a really good device. Let's actually look at it. So let's plug it in and look at LSVSB. I think something showed up. Yeah. So LSUSB is going to be, I think, a mass storage device. LSUSB, USB disk. This is 110. 110. How many interfaces does it have? 1. Mass storage, SCSI, bulk only. See. So data packets. There are 2 types of data packets, each capable of transmitting up to 1024 bytes of data. Well, first of all, token packets must conform to the following format. They have a sync field, they have a PID field, they have an address field, they have an endpoint, they have a CRC, and then they have an end of packet. Okay, and then there's data packets, which can carry up to 1024 bytes of data. High-speed mode defines another two data PIDs, data 2 and M data. Data packets have the following format. They have a sync, they have a PID, they have data, they have a CRC of 16 and an end of packet. The maximum payload size for low-speed devices is 8 bytes. For full-speed devices is 1023. For high-speed devices is 1024. Data must be sent in multiples of bytes. So you can't send a bit field that is 7 or something or so. So it has to be 8 bits at a time. Okay. Handshake packets. There are 3 types of handshake packets, which consist simply of the PID. Actually, we can look at this. We can look at this happening. I think we can look at one such thing device happening. Unmount, eject. So I'm going to remove it because I think we can look at one of these protocols actually coming into life. And then I'm going to do here, and I'm going to sudo dmask w. It's so hard not to say my password as I do it. So I'm going to plug it in and let's see what happens. Perfect. So let's look at it. So where was it unplugged? Wow, that's a lot. That is a lot. Okay, anyways, so there's a USB, there's also some sort of thing happening. Okay. ID vendor, ID product. So let's see. Is that the 3460? So look at what happens. We plug it in. Volume was not properly unmounted. Some data might be corrupt. Press LAN, FSK. They'll leave that on alone. So USB disconnect that. A new high-speed USB device, number 10, using XHCI HCD. New USB device found. ID vendor, ID product, BCD device. New USB device string, product number, serial number, product, disk 2.0, manufacturer, USB, serial number, that, USB storage 1.3, USB mass storage device detected, and then SCSI host, USB storage that, and then SCSI says direct access, vendor code, product code, that's that. Attached CSC generic SGO type. You see, all of this is like control stuff that is going on. You see, and you can see acknowledgement and disacknowledgement, and then here it says it's a removable disk, and so on and so forth, basically. So yeah, the host is basically sending some data, and the device is sending back an acknowledge or a not acknowledge, basically. Okay, so cool. And the starter frame packet consists of an 11-bit byte transfer. If what happens if let's look at it here. What happens if I do if I go into here? Let's actually does that read anything? Nothing. Okay, so I want to go and copy some sort of little file into this thing. Recent. Let's copy this. Copy. And then I want to go in here and I want to say paste. What happens in our messages? We don't see anything. And if I come here and I say eject, what happens? Volume was not properly attached. So it doesn't log. But if I remove it, USB disconnect device number 11. Okay, cool. That's fine. That's fair. So that's probably something we don't understand yet, probably. Okay, so an SO frame packet will consist of 11-bit frame numbers sent by the host every 1 milliseconds plus 500 ns and nanoseconds for full plus minus 500 ns for full speed bus, or every 125 microseconds plus whatever that is on microseconds, yeah, on a high speed device. And then I don't remember about the low speed devices yet. Okay, when we think of a USB device, we think of USB peripheral. But a USB device could mean a USB transceiver device used at the host or peripheral. What? When we think of a USB device, we think of a USB peripheral. But a USB device could mean a USB transceiver device used at the host or peripheral. A USB hub or a USB controller IC device, or a USB peripheral device. Okay, so it means USB device means either the host or the flash drive or the hub that goes in between the host and the flash drive, or some transceiver type device where you have like a host connected to a host and they're talking to each other, basically, in essence. So by now we should know the sort of things which make a USB packet. No, you've forgotten how many bits we've forgotten how many bits it takes up to make a PID field already. Well, don't be too alarmed. Why shouldn't we be too alarmed? Because quite a bit of this is already handled by the IC itself. Most USB functions handle the low-level USB protocols up to the transaction layer, which we will cover in the next chapter in silicon. So most of these protocols that we are thinking about, like you see this protocol, the sync PID, how many this, what is the shape of this, what is the shape of that, what is the shape of this, should this be complemented or not. Most of this is handled at the silicon level. So basically the integrated circuit that provides the USB endpoint or the USB device to us already handles these things for us, and we don't have to be afraid, or we don't have to try and remember all of these things all the time. So yeah. The reason why I cover this information is most USB function controllers will report errors such as PID error encoding without covering this, one could ask what a PID encoding error is. If you suggested the last 4 bits of that, then you would be right. You see, so basically we're doing this so that when we get to a point where we're actually building USB devices and we see errors occurring, we can infer where they're coming from because we kind of know what is below, what is on the ground level. It's not that we're doing it because we will have to build from the ground level, but we're getting aware of it because things might happen. We might end up writing code in a wrong way. We might end up plugging the device in a wrong port. And when the host is complaining about these things, we need to know why the host is complaining so that we can actually debug those issues. So as you can see here, there's a host and it has a bus, and then in this bus there's a number of devices, a USB device, USB device, USB device, and we can see the same on this side. We can see the same on this side. We can go here and we can do ls USB, and in ls USB we can see this host has I think we can do ls USB help. I think there's one that gives us a tree. Yeah, so ls USB tree, ls USB. This might be a very verbose output, -t. Look at that. So we have how many buses? We have bus 1, we have bus 2, we have bus 3, we have bus 4. Bus 1 seems like it has quite a few devices. Bus 2 seems like it doesn't have that many devices. And then we have bus 3, which has like 3 devices. And then we have bus 4 that doesn't have devices. And as you can see here, this is the shape that is being shown here. This is a shape. We have a host and it has all of these sub devices on it. This is the same shape that is being shown here. So a bus, and there's many devices, and each device has endpoints. And we can do this H. If we do something like, so if we do something like this for one device, okay, so 110 is gone. 110 is gone. What if we do 3 1? What is a 3 1? Cool. So you see, this is quite a long one. What does it do? It's a Linux Foundation. It's a root hub. It's a XHCI host controller. And what does it have? It has an interface. It has a full speed or root hub interface and such and so on and so forth. And it only has an EP1 in. And EP1 in is when we want to do what? EP1 in is when we want to read from the device. We use EP1 in to read from the device. So we can't write to the hub, I think, because it doesn't expose something to write into, but we can read from the hub. Okay, there you go. And what if we do ls USB and then we look at something else? I actually don't mind doing this, plugging that in again. So there's that, and I think there's that USB, and then this is bus 1, 12. Let's look at bus 1, 12. What I want to see is how many endpoints. There is EP in, EP1. So this is the thing. You see, EP0, EP in, EP out, EP in, EP out, EP in, my function, and all of that. So here's the thing. We see this is couldn't open device. Some information will be missing. That's fine. It doesn't describe everything. It's like some sort of China thing. Sorry, Chinese people. But then it has how many? It has an interface descriptor, which is a mass storage interface, and then it has a subclass which is SCSI, and then it has an interface protocol which is bulk only, and then each interface, you see each interface here has an endpoint descriptor, has an EP1 out, EP2 in. You see that? And then it says packet size is max packet size is 1 by 512 bytes, and mass packet size is 1 by 512 bytes. Okay, cool. So there you go. And most functions will have a series of buffers, typically 8 bytes long, and each buffer will belong to an endpoint. EP0 in, EP0 out, etc. So EP0 in, so this is EP2, EP1, EP0 in, EP. So okay, that's fine. I see. and 0 cross 82, 0 cross 01. So it looks like these ones are always standard. 0 cross 0, 0 cross 82 and 0 cross 01 as standard, because these are the same ones we used for our no. Okay, here 0 cross 82, 0 cross 1, 0 1. Yeah, they look standard. Okay, cool. So each buffer will contain an EP1, EP0 in, EP0 out. Say for example, the host sends a device descriptor request. The function hardware will read the setup packet and determine from the address field whether the packet is for itself, and if so, will copy the payload of the following data packet to the appropriate endpoint buffer dictated by the value in the endpoint field of the setup token. It will then send a handshake packet to the acknowledge the reception of the byte and generate an internal interrupt within the semiconductor microcontroller for the appropriate endpoint, signifying that it has received a packet. This is typically all done in hardware. Wow, that makes a lot of sense now. So what they're saying is some of this will not be done in hardware, but most of this, like endpoint stuff and all of this data stuff, transfer type, NAND data, and all of this, and I think we can plug in our let's also plug in our device, so our actual Zephyr device, so that we can actually look at the Zephyr one as well. And I'm just gonna go plug it in seriously, I'm just gonna plug in the USB side of it. Okay, so it needs power basically. Okay, cool. LS USB, and then I want to do this not this V-Link 3, this one here. So 113. So 0 cross 82, 0 cross 01. So what we're saying here is, you see, all of this stuff is mostly generated by hardware. It's done in hardware itself. The hardware knows how to answer most of these questions. There's quite a few it doesn't know how to answer, like this is going to be all stuff that comes from Zephyr, and this too as well is going to come from Zephyr. But once you get like down here, this stuff like 1x16 and 1x512 and 1x512, this is stuff that the hardware itself knows how to answer for, because it's aware, the hardware is aware, so it can answer for this stuff by itself. Okay, cool. And then because there's a microcontroller, like if this was a mass storage device, I don't know if we can run a mass storage device sample. Can we run a mass storage device sample? Yeah, we can. It depends on how many samples there is in USB in Zephyr. Let's look at how many samples, because it would be nice if we can run a few samples and be able to actually change this device a few times. That's in any case the point of doing all of this. USB. So the CSEM, that's fine. DFU, no. HID keyboard, HID mouse. It depends on if this thing has there's a UVC one, yeah, for sure. We can run the UVC one with software generated hardware, yeah. Software generated established video generator. Video established generator. So we can run that. And then what I want to do here is go Control R West build. Yeah. Samples USB, I think UVC, and then I want to dash p, but I want to go like dash s video video dash sw dash generated. Let's run it and see what that changes. It should now enumerate our thing as a camera basically. Yeah, that's fine for now. And I think I need to go like that. We did the west flash. That's perfect. I would actually run the UVC thing, because if I run the UVC thing, it will crash my OBS, and I do not want it to do it. Well, we can actually do it. ls dash dev video is that, and then if I do ff play dash I dev video 2, yeah, there you go. I don't know if OBS has crashed. Cool. There you go. So anyways, we are running generated video from this device. But the thing we want to do, the thing we actually want to do is we want to do ls USB, and then what we want to do is look at the UVC sample here over here, the Nordic UVC sample, and that is going to be 114. So there you go. So as you can see here, this is a UVC device, and it defines a camera. UVC sample, it defines a video interface collection, video control, and there's all of these hardwares, and then there's an interface descriptor, and the interface descriptor defines an in, and I don't think there's going to be an EP out, because you can't write to this device. You can just read from it and such. So basically we just change this thing into another thing, and let's see, can we change it into something else? Basically what that means is there's a microcontroller on the thing that you're using as USB, and that microcontroller will usually know how to respond. And this is why USB drivers themselves can be so end up being so huge. USB drivers are quite big, and the reason is because they have to answer to all of this. So the thing that we're running right now is USB device next, and we're running UVC device next, and we're running class, and in class we're running USB UVC, and UVC is a huge class. It's quite a huge class. It's quite a huge class that needs a lot of that needs to know a lot. So the thing we're doing is we're understanding what documentation we need to do to understand, so that we can come in here and we can look at these classes and we can use them in a certain way that makes sense to everyone, or makes sense to about what is being said. Cool. Yeah, so let's now look at endpoints. Endpoints can be described as, so remember these endpoints, EP in, EP out, EP in, EP out. Endpoints can be described as sources or sinks of data. So from an endpoint, if we actually just run the CDC-SCM first of all, let's actually run the thing that was there before, samples USB UDC, and then tab, and then I want to do CDC-SCM. Okay, so that we can actually go back and source it, so that we can look at more endpoints, something with more than one endpoint. Something with more than one endpoint. And this is actually one of those unrealized advantages of Zephyr in my head, because look at how much work we can do. I mean, if this was if this was something else, we would have to do so much work in order for us to change the sample that we're running. LS USB. Especially considered we could do things like just choose 115. There it is. 150. So, especially considering we can just change, we've not even changed the hardware. We can just change what hardware it's running. If I had to run this as a video device, I would have to have a video connected to it. I would have to change pins. I would have to change a lot of things, and that would be quite like a cumbersome experience. But with Zephyr and with all the amenities provided by Zephyr, we can kind of swap between things and learn things really quickly. So, endpoint descriptor, this is what we want to look at. So this interface, this CDC data interface, there's a CDC control one as well. You see, there's a CDC control abstract modem control. This one only has one endpoint, but we're looking at this CDC data interface, and let's look at what those endpoints mean. Endpoints can be described as sources or sinks of data. As the bus is host-centric, endpoints occur at the end of the communication channel at the USB function. As the bus is host-centric, so this bus is, when you talk about USB bus, you're talking about it facing it from the host. You're always talking about it in the perspective of the host. Endpoints occur at the end of the communication channel at the USB function. So this means in the microcontroller, the thing that handles the data or the request that is sent by the host, that's where the endpoint lives. So if we can come here and we can go to USB CDC SEM, and I think we can do Control F and we can do something like endpoint. That's fine. I just want to find, is there a list of endpoints somewhere? Aha, CDC SEM descriptor. So there's a few endpoints here. There's 3 endpoints here, and this makes sense because there's a defined descriptor. There's a BNAM endpoint 1, and CDC USB desk endpoint, USB desk endpoint, USB type bulk, USB type interrupt, USB type bulk. Okay, number of endpoints here. Description, this is a CDC SEM subclass, abstract control model subclass, cool. And then what else here? And number of endpoints 2, and this is a CDC data class. And then you see there's a cross 82, and then there's a cross 01 over here, as you can see. So interface 1 in endpoint, interface 1 out endpoint, and all and so on. And basically what that document is telling us, at this end is where an endpoint occurs in the device where the endpoint is handled, where the endpoint is. Let me see if there's any questions on the chat, because sometimes there's questions and I haven't answered them. Cool. So in the device where there is actually where the endpoint, where the data or the transaction is handled, is where the endpoint occurs. Is basically what this document is telling us. As the bus is host-centric, endpoints occur at the end of the communications channel at the USB function. So inside the device where the endpoint is handled in a USB function. At the software layer, your device driver may send a packet to your device endpoint, EP1 for example. As the data is flowing out from the host, it will end up in the EP1 out buffer. Your firmware will then, at its leisure, read this data. If it wants to return data, the function cannot simply write to the bus, as the bus is controlled by the host. Therefore, it writes data to the EP1 in, which sits in the buffer until such time that the host sends an in packet. This can be seen very well in our code here. If you come down here, you'll see that we write a character, and then we say we write a character, and then in order for us to receive a character, we read a character. We don't just, there's no callback that is called for when we will get the data. There's no callback that the device will call. It's just that we ourselves as the host, because this code, this CDC host experiment actually runs from the side of the host. So as it runs from the side of the host, the fetcher, it is upon us to send the data, and if we want to reply to that data, we have to go and fetch the reply to that data. And the way we do it is by writing and reading buffers. As you can see here, we write to EP out. We write to EP out, so out of the host, and then when we want to read, we collect data, we read from EP in. These are two buffers. These are buffers that are kind of shared between the host and the device, and if you want to read or write from one of them, this is basically what happens. Okay, cool. This is becoming quite clear. Okay, cool. All devices must support endpoint 0. And this is the endpoint which receives all of the device's control and status requests during enumeration and throughout the duration while the device is operational on the bus. So all devices have to at least have one endpoint. Okay, and then there's always endpoint 0. So if we go here, let's see here. There is always endpoint 0. So there's going to be an endpoint descriptor. So let's do that, and then we can do grep endpoint. So bnum endpoints 1 cross 81 ep1 in ep1 in ep1 in out. Okay, so this is the one that can actually take this one has two. This thing has 3 endpoints, but the first endpoint is only from the host to this device. Huh? Yeah, from this device to the host, and it basically. But how do we send it control messages? How do we send it control messages? Because if that's the case, then how do we send it a control message? Or is it just not listed because it's implicitly assumed? Configuration descriptor is that, and this has that construction model, and then it has an interface association, interface descriptor. What if I say grep interface? 4 of them. Number of interfaces 2. The communication abstract modem, and CDC data unknown. Okay, cool. This is fine for now. This is fine. So all devices must support endpoint 0. This is the endpoint which receives all the devices control and status requests during the enumeration and throughout the duration while the device is operational on the device. Okay, and then there's pipes. While devices send and receive data on a series of endpoints, the client software transfers data through pipes. A pipe is a logical connection between the host and the endpoint. Pipes will also have a set of parameters associated with them, such as how much bandwidth is allowed to, what transfer type, control, bulk, or I see that here. So let's not do interface. I see that here. So these are pipes. You see, this is a pipe. This feels like it's a pipe to me because look, it says what data, what the bandwidth is, and this one as well. This one looks like a pipe to me as well, and this one up here as well looks like a pipe to me as well. Okay, so it looks like there's language here that is crossover, endpoint and pipe, and this is also a thing that I've seen in Linux and Zephyr, because there's at some point in Zephyr when we're doing video there's endpoints, but in Linux, when we're doing videos, there's pipelines or pipes, and they're sort of used interchangeably. So while a device sends and receives data on a series of endpoints, the client software transfers data through pipes. A pipe is a logical connection between the host and the endpoint. Pipes will also have a set of parameters associated with them, but how much bandwidth is allocated to it, what type of control, bulk, isochronous, or interrupt. It uses a direction of data flow and a maximum packet buffer size. For example, the default pipe is a bidirectional pipe made up of endpoint 0 in and endpoint 0 out with a control type transfer. Control type transfer. What is that thing that we, the mouse? I think it's a mouse. There's a thing on my machine that only has one. I think there's a mouse. There's a mouse somewhere here. USB keyboard, no. Optical mouse. So this is 3.2. Let's look at 3.2. So optical mouse, instant optical mouse, whatever. And what I wanted to see is the interfaces. EP in, it's an interrupt, and that's it. I don't see anyone listing a control one. Let's look at perhaps one of these hubs. Let's look at device 1.1. It's going to be giant, I expect. 1.1. I don't see where it says an interrupt. I don't see one that says its transfer type is control, basically. Can we look at the 1.5, which is the microphone I am using? 1.5. This is the microphone I am using. This is going to be huge because it's big. It's got a lot of functions that you can do over USB, and it's very well defined. So control device, that's fine. But where is the description of the packets that go into this or not? Interface, audio streaming, frames, descriptor. Wow, I do not see. Type. Isochronous, yes, that is for you see, like audio stuff needs to be timed. You can't just do audio stuff. It's just not that. And then there's an interrupt one, and I guess the interrupt one is the control one. Well, not really. Control, bulk, or interrupt. It uses a direction of data flow, maximum bucket, and so on. USB defines two types of pipes. Stream pipes have no defined USB format. That is, you can send any type of data down a stream pipe and it can retrieve the data out the other end. Data flows sequentially and has a predefined direction, either in or out. Stream pipes will support bulk, isochronous, and interrupt type transfer types. Stream types can either be controlled by the host or the device. Okay? Because if you're like using it as a source of data, then the microphone needs to be able to control that thing, or the host needs to be able to control that thing. Message pipes have a defined USB format and they're host controlled, which are initiated by a request sent from the host. Data is then transferred in the desired direction dictated by the request. So if you want to write to the device or you want to read from the device, it will do the respective thing, the correct thing that you need, probably. Therefore, message pipes allow data to flow in both directions, but will only support control transfers. Okay, that is pretty cool. We have a couple of more minutes, 16 to be precise, because I promised myself I'm going to finish at 5:15. And I think we can look at endpoints. I don't know how long endpoints is. This is quite long. This is quite long. This is quite long. But it has mostly images. Let's quickly peruse them so that the next time we're here we can actually jump all the way to USB descriptors, because these are going to be interesting ones. Now we can actually start looking at what the device is, what it has, and know what all these numbers mean, and why they belong somewhere and why they don't belong somewhere. And probably at some point we start developing a driver as it is. It's not going to be all like I'm reading out as I'm doing this. So it's just it's not going to be all lectures and stuff. So let's quickly control transfers. Control transfers are typically used for common command and status operations. So these are endpoint types. Okay, cool. Yeah, control type. They're typically used for command and status operations, and they're essential to set up USB device with all the enumeration functions performed using control transfers. They are typically busty random packets which are initiated by the host and use best effort delivery. The packet length of the control transfers in low speed must be 8 bytes, high speed can allow 8, 16, 32 or 64 bytes, and full devices can go up to 64 bytes. So this is just which endpoint types. Okay, cool. And then the next one is going to be, I'm not going to look at that. Those are control. Interrupt transfers. Anyone who has had an experience of interrupt requests on microcontrollers will know that the interrupts are device generated. However, under USB, if a USB device requires the attention of the host, it must wait until the host pulls it before it can report that it needs urgent attention. So, interrupt transfers, guaranteed latency, stream pipe, unidirectional, error direction. So interrupt transfers are typically non-periodic, small device initiated communication requiring bounded latency. An interrupt request is queued by the device until the host pulls the USB device asking for data. So if my microphone needs me to know something, it will put some sort of interrupt transfer in the pipe, and we saw something like this here. See endpoint descriptor here. This is an interrupt type. Basically, if my microphone needs to know that it's run out of battery or something of the sort, it can put that, it can write that into a buffer, and whenever my host tries to talk to it next, it will encounter this interrupt and it will have to deal with that before it goes on with anything. So okay, cool. Isochronous transfers. The isochronous transfer occur continuously and periodically. They typically contain time-sensitive information such as audio or video, and if there were a delay or retry of data in an audio stream, then you would expect some erratic audio containing glitches. The meat may no longer be in sync. However, if a packet or frame was dropped now and again, it is less likely to be noticed by the listener. So the deadline is more important than actually delivering everything, because you don't want some laggy thing. Humans can only perceive at a certain rate, and even machines themselves can only perceive at a certain rate. So if you are, and this is where like one of those Nyquist things comes in. If you're transferring data at a Nyquist applicable rate, which is if you want to transfer 50 megs per second, you transfer at 100 megs per second, so that if something is lost, you get the next packet and you don't realize that you lost anything in the way. So those are isochronous transfers. And then there's bulk transfers. Bulk transfers can be used for large busty data, such examples could be used a print job sent to a printer, or an image generated from a scanner, or bulk transfers to provide we can copy from a if we plugged in, I'll unplug that, and then I'll do this, and I'll plug in my flash drive again so that we can actually see it, and ls USB, and we can look at this USB disk. This is 116. If we look at 116, what we'll see here is that it only has a bulk endpoint out and a bulk endpoint in. So it's just basically large stuff. You can copy big things into this thing and copy big things out of it, and bulk transfers provide error correction in the form of a CRC16 field on the data payload and error detection retransmission mechanisms, ensuring data is transmitted and received without error. Okay, so I'm gonna stop there today. And the next time we're gonna look at USB descriptors. Probably we might look at them in the context of going through. What we can't do is, the next time we look at this, we can go through USB CDC and Control F descriptor. descriptor. And what we can do is we can go through all of these USB descriptors, so such as the ones defined in USB CDC SEM, and we can actually start looking at each one of them. The thing is, once we we can go to this one and we can look at it, and we can always go back. So IID, we can look at that one. IFO, we can look at that one. So these are the things that are in here. So we can go through this code as we understand the code that is coming through in the other side. And now I'm actually starting to understand why these files are so huge, because this one itself is 1,300 lines. Actually, it's not that huge, to be honest, because if you remove the descriptors, which you already kind of sort of know, if you remove the descriptors, then it becomes a very small file. It's not that big, it's not that hard, it's just a tedious thing to go through and make work right. And then at some point, we will know so much that we will be able to come back and start writing drivers. And I think the one driver that I want to write is the test, the TMC, USB TMC, USB TMC class. So USB TMC test and measurement class specification. So this is for basically turning devices into oscilloscopes. Basically, we can make a logic analyzer by implementing this on a device, and we can read from pins on it. That would be awesome, because if we can implement a USB oscilloscope and somehow on the device also maybe even connect it to Pulse V or something of the sort, it would be quite amazing. Anyways, my name is Zach. This has been a very long lecture. We've been sort of discovering USB descriptors, USB protocols, and USB endpoints. It's been good to jump through the code, jump through some documentation, start to understand and start to make sense of all of these things. Thank you so much for those of you who came by. I don't expect that there's anyone who has any questions at the moment, because I think a few of you have dropped off. And thank you so much for coming to this. And if you're watching this after the fact and you are trying to understand something, let me know. Leave a like, leave a subscription, join our Discord community, and we can always learn together and do things together. And thank you so much. Remember to be daring, and see you again tomorrow. Thank you. Cheers. Day 1 of December has been done.